Hello everyone, and welcome to another lecture number 3 of the course Artificial and Robotic Vision Systems in spring 2013. Again, my name is Eugenio Culurciello. Today we will be talking about convolutional neural networks and model of the visual system. So convolutional neural networks, like we saw in the previous lecture, are basically the workhorse of this course. Remember, we were talking about neural network in the previous lecture, where we had multiple possible classes like a pedestrian or a car or a motorcycle or a truck or something else. So this is kind of an example diagram of the neural network that was exemplifying this kind of operation. What we want to do is we want to be able to detect multiple classes. Again, we don't have to detect multiple classes. We can have just one class, for example, a face detector. But that might be, a bad use of convolutional neural networks in the sense that they might require more computation than using some specific trick for just one object. Nevertheless, convolutional neural network, even if for just one object, they recently reported some of the best results, for example, in traffic sign recognition or pedestrian detection, and these are all results from Yann LeCun. In any way, COMNETs, or convolutional neural nets, or how we call them, COMNETs, are basically the most important part of this course. So it's extremely important that you all understand exactly how they work and how they perform the job. So please pay attention to this lecture and the next lecture. There are also about convolutional neural network and also the example that we're going to give. So these are not only the main workhorse of this course, but they're also the main component of deep networks and deep learning. And you might have heard about deep learning and big data recently. They became very popular. What it means is if you have to process a lot of images or a lot of videos or a lot of audio, you might need techniques that very effective, like the deep learning, that is basically one of the best techniques in machine learning right now. So most of these use some kind of a neural network, large neural network. Convolutional neural network is just a special case of it. So I have to say that convolutional neural networks were pretty much invented and pushed forward significantly by Yann LeCun. Yann LeCun is a professor at NYU, which we have the pleasure to collaborate sometimes. And this paper from 1998 basically summarizes a lot of his work, where he applied this to document recognition, in particular to letter recognition. Convolutional neural networks were used at the time to analyze the checks and other things, handwritten characters, numbers and letters, in particular numbers, and they were used here as an example to recognize, for example, checks for a bank. And they've been this system that was developed by Yann LeCun and Leo Boteau and Yosha Benjo were all working at Bell Labs. It became quite popular and it was commercial for a while. This is part of the history of neural network, and is that it was very difficult to train very large and deep neural network like this one, so multiple layers, because there were really no techniques to be able to train them. And Yann LeCun was one of the first people that really invented one of these backpropagation and optimized it. An algorithm that can perform gradient descent and learn these how to train these networks, basically. So if anyone is interested, I highly recommend to read this paper from 1998. Maybe not the whole thing, but at least section 1 and section 2 that explain convolutional neural network and all the details, and pretty much they'll do the job that will explain more or less what I will introduce in this class as well. So, talking about convolutional neural network as invented by Yann LeCun, I want to present to you this diagram. This is basically a schematic representation of a convolutional neural network as it typically operated, as a traditionally operated. So the original neural network in the previous paper from Yann LeCun was more or less of this shape. So convolutional neural network have layers. So combination of operation that we call layer that are repeated. So this is layer 1 and layer 2 probably have very similar operation. There could be multiple layers like 3, 4, or 5. And then at the end there is a classifier that basically classifies the features that are extracted by these convolutional neural network layers into the final answer. For example, this could be an input. A convolutional neural network have an input, so for example the 32 by 32 image of a character or a letter character or a piece of a letter or something. They perform an operation called the convolution, which I'm hoping that most of you are familiar with. If not, I would really highly recommend you to look it up. It's a standard time domain operation performed in signal processing, basically. So the input image is convolved by a convolution operation to produce multiple feature maps. So the input image is convolved by as many maps as you want of filters. So in this case there's 6, so 6 maps are actually, the input image is convolved by 6 convolutional filters and produces 6 maps. The second step of the convolutional neural network is subsampling. So from this map, which is quite large, by the way, notice that this map has a little bit, the size is a little bit less than the input map. What you usually do is to try to ignore a boundary condition. With the convolution, you wouldn't be able to convolve this pixel, for example, because half of the pixel at the border, because half of it, half of the kernel space is basically lying outside. So in order to avoid problems at the border, you just try to convolve the pixel that are completely, they can be centered completely by the convolutional mask. So that's why the size decreases. Basically, if this is a 5 by 5 convolution, you usually lose 2 pixels here and 2 pixels here on each side. So that's why you go from 32 to 28. The second operation, as we said, is subsampling. So we want to try to reduce the dimension of the image, and then you get to a smaller version. So for example, you can subsample by 2 by 2 by averaging 4 pixels, and you get an image that is half the size. And this image, it basically goes through a nonlinear operation to separate one layer from the next layer. The reason why these operations are done, I will explain it more in the following slide, the following lecture, is well, one of the convolution is basically trying to look for specific features in the image. The image is convolved to produce map because the same feature might be anywhere in the image. There might be multiple features that we're interested in, many more than 6. For example, 6 might be a good number, and they were used in 1998 where computing power was still fairly low. So to process an image of 32 by 32 by 6 filter took quite a long time, not as today, which a network like this would run much faster than real time on a laptop. So convolutional neural network, each layer basically perform a convolution, obtain some filters invariant to the position, because you were trying to find this filter by convolving the kernel anywhere in the image, and then you were trying to become independent of size by reducing the feature size, by subsampling the image and making it smaller, basically, so that it can be processed by the next layer. The idea of making the image smaller is one, because in the next layer you might want to find features that are larger than what are found here. So, for example, if the input image, this filter is 5 by 5 and we're subsampled by 2, in the second image, when you do a convolution, then this is sort of the equivalent of a 10 by 10 filter, and you can think of it like this, basically. Operations are repeated from one layer to the next layer, more or less in about the same kind of format. So again, you have, in this case, you have multiple inputs going in. You will do a convolution. You will create multiple maps called C2 maps. In this case, 16. Again, you lose, these are 5 by 5 convolution, and you lose 2 by 2 pixels, so you get a 10 by 10. And then you perform again subsampling, and you get a feature map. And you go through again a nonlinearity, which is generally an hyperbolic tangent. The reason why you want to go through a nonlinearity in both between layers is because if these are all linear operation, if you are continuing to apply a linear operation, then all of this might fall. All the network might be able to be represented by a linear operation. So you wouldn't have two layers, but you would have just a single layer that performs both of operation in some cases. So it tries to really figure out features that this nonlinear operation tries to push these features to higher values. So it makes them stronger if they are strong features, and it weakens them if they are not that important. So it really tries to break a barrier. It tries to detect features that might be interesting. For example, here you could think of it as oriented filters. In the second, instead in the second map, you might think of it as combination of oriented filter, like a corners and something like this. The final classifier will just get the final features from the convolutional neural network and perform a classification. So, for example, if we are interested in obtaining 10 categories, for example, one for each number, then that's what we would do. So the classifier is again a two-layer neural network, so it's very similar to what we've seen last time. It's can be seen as a perceptron, it could be fully connected and so forth. It can also be replaced by support vector machine or other classifiers, but I don't really see the point, since the entire network is a neural network. We should probably keep the final classifier as a neural network.